As we said, this is our team meeting, and I will be taking the technical presentation for today. So, before we begin the technical presentation, I would like to reiterate that we have an upcoming training on solar PV system design, as we can see over here. And this training is scheduled to kick off on the 25th of October 2025. It will run for a period of 7 days, which means it comes to an end on the 31st of October 2025. Now, of course, as we usually do, the first day of the training is totally free. So if you're interested in joining the training, you can send a message to us using these contact details displayed on the screen. So today's technical presentation is going to be on something that is usually left behind in ETAP software studies. Yet, it quietly determines how accurate our entire analysis will be. And I'm talking about grounding and earthing. So, in most projects, we spend time running analysis such as the load flow analysis, the short circuit studies, the protection coordination studies, and arc flash studies, but we hardly ever stop to ask, what kind of grounding system are we actually modeling? So, this technical presentation is titled The Forgotten Foundation, Grounding and Earthing in ETAP Power System Studies. My name is Ekwe Jesse from JP Smart Solutions Limited, and we'll be taking you on a detailed insight of grounding and earthing in this technical presentation. So, what are we expecting? The outline. We are going to start by establishing a fundamental concept of what ETAP grounding or earthing really means, and then we jump right to why most users ignore this grounding or earthing. Because it is very common, we actually ignore it, and there is a reason for that. There is a reason for everything. So I'll be explaining why it is usually ignored, and then I would explain why it really matters. We would also be giving a practical illustration of the effect of grounding and earthing using ETAP software. And lastly, we'll talk about ETAP tools for grounding analysis. So let's begin with the first question. What is this grounding or earthing actually all about? Now, in ETAP software, grounding or earthing is not just a label. This is a misconception we have. It is not just a label. It defines how faults return to the source. It defines how our protective relays operate. It also defines how safe our electrical installation will be. Not just a label. I will illustrate that using ETAP software. Now, the software allows you to set things like the system grounding type. We can have solid, resistance, reactance, or ungrounded systems. We also have the ability to set the earthing method for each load, such as the TNC, the TNS, the TT, or the IT. We'll go into earthing methods in details maybe some other day. Now, you can also specify ground conductor data, soil resistivity, and electrode resistance. Now, all of these determines the reference point of your network. Unfortunately, most users, most engineers skip this step. Now, the first thing they do is they build their single line diagrams, and once you're done with your single line diagram, you carry out, of course, a load flow study, because load flow study validates your project model, which is your single line diagram. So once the single line diagram is built, you start running your studies, your load flow, your short circuit, and you assume that ETAP's default grounding is good enough. But that single assumption can alter everything that follows. So now let's talk about why most users ignore this grounding. Why do engineers ignore grounding in ETAP software? Practically, there are three main reasons. Now, the first reason is our focus tends to be on visible results. By visible results, I mean things like voltage profiles, the fault currents, or the coordination curves. So, grounding feels like a background data as it is not displayed on any result. Secondly, we often do not have the data for soil resistivity or grounding electrode, so we can just skip it. The data is unavailable, so why should we stress ourselves for that? And thirdly, there is a general misconception. Grounding does not change much. So we have this mindset that it is more of a construction issue than an analytical parameter. Now, the result of ignoring grounding is that we actually end up using default grounding types. In some of our previous sessions, we've explained why you should avoid typical data. So in this case, when we ignore this grounding, we end up using default grounding types of equipment, which may not reflect the real system at all. That is why you can carry out a short circuit analysis, and what is in reality is quite different from what you have in your simulation. And this can lead to dangerous assumptions when those results are used for protection settings or arc flash labeling. Now let's move into why grounding matters. This is why grounding matters much more than most people realize. First, it directly affects how fault current flows. Whether it returns through the neutral, through resistance, or through the earth itself, grounding directly affects how the fault current flow. Next, it influences the fault magnitude. And if it influences the fault magnitude, it means that it also influences the relay sensitivity. If it is influencing the relay sensitivity, it means that it is also influencing the fault clearing time. If it is influencing the fault clearing time, then it also means that it is influencing the incident energy level. That is when we come to arc flash assessment and mitigation. So, for example, a solidly grounded system will produce a large ground fault current. A high resistance grounded system will limit that current drastically, but it also affects the relay pickup settings. So ignoring these differences means that your relay coordination might look perfect on paper. It may look perfect on your simulation, but in the field, it will fail. So grounding also affects safety. So when we talk of safety, we are talking about the step and touch potentials around substation grids and the risk to maintenance personnel during faults. Step and touch potential, very important for our safety, especially in our substations. So grounding is not just a detail, it is a determinant of both system performance and human safety. So let me switch over to ETAP software and give a little example. Okay, so we have two systems over here, perfectly the same. We have a power grid and the short circuit MVA capacity is 100, similar to this 100. We have it connected to an 11 kV bus bar, similar to this system which is connected to an 11 kV bus bar. We have a 5 MVA transformer, similar to this system where we have a 5 MVA transformer. We have a bus bar at 0.415 kV, which means that this transformer is stepping down the voltage from 11 kV to 0.415 kV. And similarly, we have the same scenario over here. The transformer is stepping down the voltage from 11 kV to 0.415 kV. And we have lump loads attached to both of them, rated 2 MVA each. So primarily, we can just run a basic load flow analysis to verify that the ratings of the parameters are the same. So we can see this, they're actually the same. The results on each section are the same, which means that each parameter is rated in the same way. So now, we are going to illustrate something. If we come over to this transformer, and we come over to the grounding page, now people usually ignore this. Now we can see that the primary is delta while the secondary is star. And over here we have what we call the grounding, and we can see this is solidly grounded. Solidly grounded. We can also see the earthing type over here, TNCS. Now this is the misconception I explained earlier. This is what some engineers do. See over here we have symbols, grounding elements. So we click on this. I will click OK. All right, let me come over to edit mode so we don't have results. So we can see this is for the primary, which is delta connected, and this is for the secondary, which is star connected, solidly grounded. That's why we have this guy over here. We can come over to this guy here and do the same thing. I will just check on this guy, symbols. So it is just showing us the configuration, telling us that the primary of the transformer is delta, while the secondary of this transformer is star, which is solidly grounded. So let's carry out a short circuit analysis over here. So we run a short circuit analysis with bus 2 faulted and bus 4 faulted, and we can see that we are having the same results. We are actually in line to ground fault. Since we are talking about grounding, we are paying attention to the line to ground. So we are looking at the same results, the same grounding system, the same results for the same grounding system. Now what happens when we slightly alter? Let's change the grounding system of this guy. We come over here and we said, okay, instead of it to be solidly grounded, let's have a resistor as the grounding element, and we have 10 ohms, a resistor of 10 ohms, and we click on OK. So you can see the diagram has changed, the symbol has changed, indicating a resistor. I can zoom in. It has changed, indicating a resistor before the ground. Okay, maybe I can take this guy over here. Yeah. So we can zoom to fit page. All right. So we have a resistor in this case, and in this case it is solidly grounded. And we carry out the same short circuit analysis according to IEC 60909 standard. Now, we can see that the short circuit magnitude over here is 0.025 kiloamps. While over here, The short circuit magnitude for a line to ground fault is 81.374 kiloamps. See the large difference just because I changed the grounding type. So imagine in your system, you use this, let's assume in the actual power system, in reality, it is grounded through a resistor, and you, in your modeling and analysis, you actually carry out the grounding as default solid grounding. So it means that it will affect all your results. Your short circuit results are affected, your relay coordination results are affected, your arc flash results are affected because the magnitude of incident energy is relative to the magnitude of short circuit current at that location. So this gives rise to the crucial need to pay attention to your grounding while modeling equipment. This doesn't just apply to transformers. Across all equipment you are modeling. The same system, the same line, the same transformer, the same voltage, but a very large difference in fault current. So if you use the same relay settings for both systems, the relay on resistance grounded feeder might not trip at all because the current will never reach the pickup level. Imagine we are having 81.374 kiloamps over here, and here we are having 0.025. So using the same settings, we'll be looking out for this guy. Meanwhile, this is what we should actually be checking. So this shows how neglecting grounding can lead to false conclusions in our fault studies and protection coordination. Grounding type is not a small checkbox. It is the difference between a tripped feeder and a hidden fault. Let's switch back to our PowerPoint. Okay, so let's move over to ETAP tools for grounding analysis. It's not just our short circuit study. Now, the first tool is the system grounding and earthing manager. This allows us to define the overall grounding configuration for the entire network or per subsystem, just as we were doing in the previous illustration. Secondly, we have the ground grid design and analysis model. Now, this is extremely useful for substations as it calculates what we call the mesh voltage, the step and touch potential, which we mentioned earlier, and verifies compliance with the IEEE 80 standard or the IEC 60479 standard. Now, this is a feature embedded in ETAP software, ground grid design and analysis model. So thirdly, we have what we call the protective earthing sizing tool. It ensures that your ground conductors are properly sized to carry the expected fault current safely. And finally, we have the arc flash and safety assessment model. Now, all these other settings integrate directly to the ETAP arc flash and safety assessment models because we are going to be using this as a point of reference. As I said earlier, it affects the incident energy. So it will affect your arc flash results, your arc flash labels. So if your grounding data is wrong, your entire arc flash energy calculation could be wrong. These tools are there on ETAP software, but then many engineers never even open them. So as we round up, let me share some actual real-world implications. Now, in one refinery study, engineers found that incorrect grounding assumptions led to arc flash incident energy values being off by 70%. Just as you saw in our short circuit illustration, the large difference between the fault current affected the arc flash results. In another case, a substation design passed all electrical checks, but then it failed inspection because the grounding grid resistance exceeded 1 ohm, something that would have been caught earlier in ETAP's ground grid model. We have a training upcoming which is on solar PV systems. In solar and inverter based systems, proper grounding defines the system's voltage reference. Without it, the system can float, causing unpredictable behavior and communication errors in controllers. So grounding doesn't just affect protection, it affects measurement, safety, communication, and compliance. Every time you export any ETAP result for a project, ask yourself this question: did we model the ground? Did we model the ground? Very important question. So let's wrap up. Now we have 3 key messages for you. The first, grounding is not optional. It is a core part of your ETAP model. Secondly, it influences protection, arc flash, and personnel safety much more than most realize. Thirdly, always model, verify, and document your grounding system before finalizing any study. When you start paying attention to grounding, your studies become more accurate, your protection more reliable, and your installations become safer. Remember this simple truth: the strength of a power system lies not only in its conductors, but also in the part beneath your feet, the one you do not see. Thank you all so much. We are done with the technical presentation for today.